You got it to be okay like that. Shoop, shoop. Okay. Cool. So we got through 3.6. That's what that test was on. So we're into 3.7. I'm going to focus in 3.7. I'm going to focus on the what's called the kinematic problems, the velocity, the position, velocity, and acceleration stuff. And then I'm going to just take questions as you do the homework if they come up, because then they have examples of all the other kind of stuff you might see in this homework. They have an example that's pretty much exactly like what they're going to ask you. So it's the age-old thing about, if any of you guys are going much further in math, I don't think I've said this yet, you eventually get a book. It's really thin, and it still costs $180 or something. And you flip through and you look at the chapter, there's concept, 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 and then problems, and there's no examples. So while you are still with a book that has examples, appreciate the shit out of that. All right? At least look at the examples if you're not going to read through anything else. So tell me this. If I give you, you already saw this in an earlier section. If I thought you were my good marker. If I give you a position function, what is the, how do I get the velocity function? Yeah, the derivative. So if I give you, position is very often, they use an S for that. I don't know why, to be honest. But I think there was one earlier, I can't remember exactly what it was, but it's something like 2 sine pi t plus 3 cosine pi t, something. Remember that? Something like that in that section where I had to make a table of values and stuff. Investigate limits. Or figure out the average velocity, I think this one was. How would I develop the velocity function then? What would I do to this? Like you just said, take the derivative. So I would do d by dt of this. I would attack this with the derivative. Because of course, what's velocity units, for example?
Distance per time.
Yeah, it's distance divided by time, right? Yes?
What's the very end? It's 3 cosine what t?
Pi t. They're both pi. Yeah. So very often you'll see a pi multiplier, so the inputs can be like 1, 2, 1/2. Okay. And this is going to give me the velocity function. Velocity is the derivative of position. It's how position changes over time. That makes complete sense. That's what velocity is. Now realize this about velocity. Velocity can be negative. A negative speed doesn't make any sense. You're backing up, you're not going negative so many miles an hour. That's weird. Yes?
Can you repeat that? It's velocity is the derivative of what?
Right here. So, velocity, derivative of position over time. Change in position over change in time. That's exactly what the idea of velocity is, right? How much does your position change over time? How's everybody so far? Is that decent? Okay. And so what would that be for this specific function? Yeah, it'll be 2 cosine pi t. What's going to happen with this? Right? It's inside the sine, so what's really happening? It's the what rule? Chain rule, because you got something inside of something else. It's not just t. So it'll be 2 cosine pi t times pi. So it'll be 2 pi cosine pi t. The root of cosine is negative sine, and the same thing happens with this guy, right? Chain rule again. So it'll be minus 3 pi sine pi t. And then I can ask you questions about what's the velocity at time t equals 2 seconds, or whatever the heck the units are. Are you guys with me? All right. And let's do one more derivative, and then I'll ask some questions. What would one more derivative be? Acceleration. I love it. The change in velocity with respect to time, which would also be the second derivative of position, right? Because velocity is the derivative of position. This would be the second derivative of position. No big deal. That would equal, what's the derivative of this guy now? Yeah, negative sine, and then you're going to get another pi pop out of there, right? So negative 4, negative 2 pi square sine pi t. The same thing is going to happen here, right? Sine, the cosine doesn't change the sign. So minus 3 pi square cosine pi t. Here's something people don't normally hear. If I took one more derivative, there's an actual name for that. And whenever I think about this, I always think about my first car. The next derivative that tells you how acceleration changes is called the jerk. And if you ever had a really shitty car, you step on the gas and it goes, okay, maybe, and I'm like, yeah, I call that the jerk. That's how the acceleration's not smooth. It's like, that's the jerk. We're not going to worry too much about the jerk, right? I like that. Some of you guys are like, oh, that's my nickname for you, Jeff. Oh, okay. That's all right. So now I can ask you several different questions. I could say, what's the velocity at 2 seconds? Let's say that position is in meters and the time is in seconds. Velocity of 2 would be how fast was it going at 2 seconds? Right, so you would just plug a 2 in to the velocity function, not a big deal, right? So figure that out real quick. So sine of 2 pi is 0. Cosine of 2 pi is 1. So you get 2 pi times 1. So you get 2 becoming 2 pi. Watts? In units of this. Meters per second. ds dt, so meters per second. Hello. What about, I should be working better. A little bit. What's the acceleration? I didn't even put a of t here. What's the acceleration at 2 seconds? Yeah, so now it'll be sine here. So that's going to be 0. Cosine of 2 pi is 1 again. So it's negative 3 pi squared. What's? Meters per second squared. It really is, if you think about it like this, it makes a little more sense. It's meters per second, which on first glance is like, the shit. But of course, acceleration is how much your velocity, meters per second, is changing per time. So it's the change in meters. So every second, your velocity is decreasing by 3 pi squared meters per second at the second. Oh, you gotta love that shit. So after 2 seconds, this particle's velocity is decreasing by 3 pi squared meters per second every second. You guys can follow that? You guys see what I'm saying? If there's an acceleration, that means that your velocity is changing in a certain manner. Is this acceleration constant? Is the acceleration constant? No. I love it. So that's why I have to say at 2 seconds, the acceleration is this. Yes?
At the very end, the last line, is it meters per second over what?
Meters per second.
Okay.
And how do I know that? Well, what's this? dv would be meters per second. How much the velocity changes is meters per second. Now, of course, that's normally referenced as meters per second squared. In case you've done any physics or anything, that's what it is. And if you think about it, that doesn't make a damn bit of sense. What the hell is a square second? No second cube, no second real. Oh, so nice. And cover the floor, square second. What the shit is that? All right, maybe. This makes more sense, but that's easier to write and say. Okay, maybe. No, what's happening? Where am I losing? It's the units, that's fine. Get over that. It's okay. It's not a big deal. I really want you to realize acceleration is this velocity changing over time. That's why that makes sense. Velocity is meters per second. How much that's changing per second. I like it. Now let me push this a bit. So if the acceleration stayed the same, let me see. If my velocity wasn't changing, how do I say this? Like 1 second later, can I estimate how quickly I should be going? If I assume that this holds for that second, at least, now watch. The minute I go past 2 seconds, will the acceleration be the same? No. But if the acceleration did stay the same, 1 second later, I should be going 3 pi squared less. My velocity should be 3 pi squared less. You guys, that's what this says, isn't it? At 2 seconds, I'm losing this much velocity per second. So let's check. Let's check. Again, let me say this again, because this is important. I mean, calculus is all about doing the calculations, but then it's understanding what the shit you're getting at the end. So 1 second later, if this held true for the whole second, 1 second later I should be going this much less. I should have this much less velocity. At 2 seconds I have that much velocity, right? 2 pi. You guys would, at 1 second I have 2 pi meters per second. Okay, I like it. 1 second later I should lose this much roughly. It's not going to be this much, is it? Because is the acceleration staying constant? No. All right, let me do it and see if you guys get it, because we're going to do this kind of thing when we get into related rates. So what is the velocity at 2 seconds? What's the velocity at 2 seconds? 2 pi meters per second. I love it. And you're not used to it. You wouldn't be saying, let's go 20 pi miles an hour home, okay? Fine. What the shit? Let me see your scale and your... you have a trigonometric scale. So yeah, but this thing, however it moves, it's 2 pi meters per second at 2 seconds. What changes that velocity is acceleration, of course. That's the whole thing. That's what acceleration's job, is to change the velocity. So 1 second later, it should be an estimate to see 2 pi minus this. That's what the velocity should be. Well, let's see, what is the velocity at 3 seconds? How would I figure that out? This might be too big of a step for this. But oh well. What is the velocity? How would I figure out the velocity at 3 seconds? Just plug it in. I love it. So it'd be 2 pi cosine of 3 pi minus 3 pi sine of 3 pi. Now what is cosine of 3 pi? -1. So -1 times 2 pi is -2 pi. And of course sine of 3 pi is 0. So this will be -2 pi meters per second. That's the velocity at 3 seconds. Which is, of course, -6.28 roughly. Is that cool? So I was going 6.28 meters per second, and now I'm going -6.28 meters per second, 1 second later. All right, can you guys absorb all that? That's exactly, at 2 seconds I'm going this fast. At 3 seconds I'm going that fast. I just had to plug 3 into a freaking equation, so it's easy. Is that cool? There you go. So I'm going this, and now I'm going that. What is -3 pi squared? Somebody, that should be how much my velocity would change if this stayed constant, and we know it doesn't. But let's just see how close this is. What is -3 times pi squared?
-29.60.
Yeah, so if you do 6 minus that, 6 minus 29, you get -23, which is not this. But it did decrease, didn't it? Now, so the point I'm trying to make is, do you see, I don't know if you guys heard me, but 2 seconds to 3 seconds. That's a huge step. You guys get what I just said? This thing is moving according to cosine pi t sine. How much will this change going from 2 to 3? Isn't that half a cycle? Isn't that like, hello, half a cycle? So that's a huge step. That's a big change. All right, maybe I'm gonna let this go for right now. I'll try to bring it back with related rates. I was gonna try to do one more thing with you guys, where instead of going 1 second, I go 0.1 seconds. Would this be a better guess then? Yes, because the less time, it wouldn't change as much from this. It should be a better estimate. But let me wait until we get some better numbers to work with, and maybe the numbers are freaking out. I don't know. All right. So on one level, is it easy enough to know how to get, if they give you a position, you should know how to get velocity and acceleration? Yes?
So if we were given the variable within sine and cosine degrees instead of something like a radian, as in like pi over 6 or pi over 3, would we just have to do that conversion and then go ahead and take the derivative of that?
If you were given, say it again, sorry?
A degree.
Oh.
So like 30 degrees. And so would we have to substitute in pi over 6 so that would be more simple? Or?
Yeah, considering that if this was like pi t squared, wouldn't the t come out with a chain rule? Wouldn't it be like 2t coming outside? Does that make sense? So the minute that this could possibly pop out, you want to use radians only. And in fact, it's going to tell you if it's supposed to use degrees, because that's a weird situation to be in. In fact, if I had an equation where percentage was something I would plug in, I'm going to change that to a decimal, period, because that's the real number. The equation's got to go, oh shit, wait a minute, leave it in percentage form, because that's how we made the equation. It's got to tell me that. That's a weird thing. So here, degrees is actually a weird thing to use, because the radians is a true measure of distance. Degrees is something we just totally freaking made up, right? I know on one level we made all this shit up, but yeah. All right, let's do this. Let's try a problem out of the book just to show you how this stuff works. Ooh, I like it. I want to show you the kind of questions they're going to ask, and they're going to be the same kind of questions I'm going to ask you. So if I give you this is my position function. They use other things besides s, apparently. So yeah, something moving according to this. I think that's what it is. Yeah. Let's see. Yeah, T is in seconds, S is in F is in feet. I like the F for feet. These units are a part of these problems. Let me ask you, let's see. Ooh, that's a good one. I like that E. It's kind of gross. So try to get as far as you can with these questions. Bless you. Ooh, yeah. Yummy, yummy. Part E is probably. Throw you off a bit. Let's see, what's velocity? What do you have to do to figure this out? What rule do you have to use or could use? You gotta take a derivative, you can use the quotient rule, I love it. If you prefer to bring that sucker up and use product rule, that's fine. Either way you do it, what do you get at the end? Oh, yeah, on the bottom, I'll do the bottom. There you go, I did half of it.
Negative 9 t squared plus 81.
Yeah, so negative 9 t squared plus 81, but what can you do? So now, and then this is easy enough. Is everybody cool with that? Yes? Okay. And then if you plug a 1 in, you get this. So what do you get for that when you plug a 1 in? On the bottom, you get 100. And on top, you get 81 minus 9, 72. So you get 72 out of 100. What's?
18 feet per second.
Feet per second. And then you can do whatever the shape was. 0.72 feet per second, right? Is that okay? Just plugging a 1 in? What's going on, guys? Is everybody cool with this derivative? Do you want to see the steps for this guy? Yes, okay. So can I see the steps? So it'd be 9t prime, right? Top first, times t squared plus 9 minus 9t times t squared plus 9 prime, all over t squared plus 9 square. Is that cool? So are you working? You, yeah, all right. Sorry, this is the good. So nice when you have a life where you're easily amused. So yeah, you get 9t squared plus 81 minus, yeah, because this is 9 here, right? Is that cool? You distribute. And then here you get 2t times negative 9t is minus 18t squared. Is that cool? Because this derivative is 2t all over t squared plus 9 squared. And then here you get, so you get 81 minus 9t squared over t squared plus 9 squared. Cool, just quotient rule. Top first, so you do the derivative of the top first. That's the most important part of that. That's why that's the only song I'm going to make. And then you just plug a 1 in into that sucker for part B. What about part C?
Set equal to 0.
Yeah, set the velocity equal to 0. It's at rest when it's not moving, and velocity is a measure of how quickly it's moving. So if I set this thing equal to 0, I just have to do what? The only way that a fraction can be 0 is if the top is 0. And the top, I can factor, or you can take the square root eventually, right? So I have to remember they said this. Yeah, normally t is greater equal to 0. It's known as t minus shit, right? Nothing's happened until t equals 0, then stuff happens. So you get t equals plus or minus 3, but of course the negative doesn't make any sense, so you get 3 seconds. So when is it at rest? After 3 seconds, it's at rest for a second, for like that, an instant. It's at rest. I could ask you, does it turn around then? Does it move in the opposite direction after that 3 seconds? And if, and you know, people take this wrong when they say this, but it's just too damn bad. If you had a half decent freaking pre-calc teacher, then they should have told you about something called multiplicity. It's going to become very useful in this class too. Anybody never heard of multiplicity except as a movie by Michael Keaton a long time ago? If you never saw it, you should see it. Multiplicity, if I say that, it's okay to not know, because I can see a lot of you don't know. So who's never heard of multiplicity before? Anybody? Oh shit, all right. Is everybody cool with this? I'm going to factor this sucker. Where'd it go? Okay. So here I can see the 3 and the negative 3 right there staring me in the face, right? These both have multiplicity 1 because they both show up once. If I put a squared there, would that have changed my answers here at all? If I put a squared right there, would it have been anything different than 3 and negative 3? No, because 3 still makes this 0. I don't care what power's on this stupid thing, right? 3 makes this 0. So what if I had 2 of them? Well, 0 times 0 is 0. So it doesn't matter if I put a billion power on this, it's still 3 and negative 3. Is that cool? Yes?
Real quick, to the left of 3 seconds, what does that say? T equals what? X? Is that cube?
That's me trying to say plus or minus 3, and then I said the minus doesn't make any sense. T's got to be greater equal to 0. At t equals 0, that's when things start happening. Let me ask you this. All right, let me take a step back. All right, let's do one a little bit easier to look at. Okay. Pre-calculus, a huge part of it is the ability to analyze the shit out of this and be able to graph it pretty well. Maybe not perfectly, but pretty close. And here, one thing we're going to do in here is improve on what you should be coming in with from pre-calculus. We're going to use calculus to make the shapes even better. Some of you guys are like, I got a calculator. Well, big deal. The very first thing you can notice that's useful for graphing is what?
X-intercepts.
X-intercepts. And then the power come into play later. So x-intercepts. And what makes this 0? Just one thing. 1. And what makes this 0? Negative 2. Doesn't matter that it's a cube. Do you guys understand? Right? Doesn't matter. It's a cube. You still make x minus 2 0 by making x 2. I don't care what power you're raising it to next. Is that cool? Doesn't change what the intercept is just because I have a different power on the root part of it. Now, when you said powers, the next kind of thing would be end behavior. Does that sound familiar? End behavior? Better. What would the highest power be if I multiplied out? Please, dear God, don't multiply this shit out. You should know. What's the highest power that I would get on x? 5th power, right? And what's a 5th power? It's not negative. Straight up 5th power. What does a 5th power look like? Right? Cubish is what I call it. Looks cubish. Or like my one colleague, like a giraffe. And I'm like, without a leg, it's going to fall over, but oh well. So I know end behavior is going to be like this. If it was negative, it would have been flipped, right? Is this starting to sound familiar, hopefully? If this sounds completely foreign to you, I'm really worried about you. Had to have gone through this before getting here. Y-intercept real quick. What's the Y-intercept? So you make x 0, right? If you make x 0, that becomes easy as shit, right? No, if you make x 0, you get negative 1 squared is 1 times 2 cubed, 8. All right. Now, let me focus on the multiplicity now. Here's the only two roots. How frequently did this root show up, though? How many times? Twice. So it's got multiplicity 2. Something squared, what does it do when it gets to its x-intercept? What does it do there? Squared thing, it turns, right? It doesn't change sign. If I put a 0 in here, what do I get for this piece? 1. What if I put a 2 in there? I get... If I put a 2 in there, I get 1. See, it doesn't change sign around its root because it's being frickin' squared. Square kills whatever sign it wants to be and just makes it positive. So it's going to touch there. See, this is the idea of the multiplicities, right? So it's going to touch at 1, 0, and of course here, what's a cubish thing to do? It goes through its root. When you cube something, it doesn't lose its sign. It's going to change sign around its root, so here it's going to go through. So really, I can get, if all I needed was a sketch, a rough sketch, here's 1, 0, here's negative 2, 0. It's going to go through negative 2, 0. Starts down here, goes through negative 2, 0. Then it's going to touch at 1. The y-intercept is 8. Right? It's going to touch it there. Bam. There's a decent, quick sketch. With very little details, but still the important things are there. So multiplicity is remarkably useful, quick tool, so I don't have to do a bunch of other weird shit. Remember we are going to do a little bit of this, but I'm going to try to let you use multiplicity. So here's my, here's like 1, yeah, there 1. Here's negative 2 and 1. It's 0 here, it's 0 here. Do you remember making these kind of things, investigating? So when you plug a 0 when you get 8, so at 0 it's positive. It stays the same sign on either side of 1, and it changes sign through negative 2. But if you put in like a 7, that's positive, that's positive. I mean, do you remember investigating that kind of thing? Putting stuff in and seeing if it was positive or negative? Do you see how it's below the x-axis here, and it's above and above? Below, above, above? Yes? Okay, and desperately needed to take a minute for this because this is going to become very important very soon. We're going to be doing similar things, but we're going to be doing them for the slope and for the second derivative and explaining what that means visually. The slope, we know what it means visually already. What the hell is the second derivative? We don't know yet. We will. So here, how the hell does multiplicity help me? I don't know. I've forgotten at this point. Holy shit. Oh, so it's at rest at 3 seconds. When is it moving in the positive direction? Well, before 3 seconds, what was that? I changed it a little bit. I said, will it be moving in the same direction after 3 seconds? What's the multiplicity on each of these? 1. So around their roots, they will change sign. So yes, right after 3 seconds, it's actually going to turn at 3 seconds. So it's just like throwing this up. It's gonna rest for a second up here, and then it actually does turn. Now there, if it didn't, I would have went running. I would have been like, what the shit just happened? You guys kind of with me? That's what it means. It rests and then it does turn around. I know it does. And I can see it real quick because of the multiplicities. I don't have to do a bunch of freaking work for that. Now this question I do have to do some work. When is it moving in the positive direction? Now for this one, if you wanted to, you could do a little 0, 3. But what was the velocity at 1 second? Is it positive or negative? Positive, right? So it's positive here, and we just said this multiplicity 1 is going to change signs around 3, so when is it moving in the positive direction? From 0 to 3 seconds. After 3 seconds, it's moving in the negative direction. So I threw it and went, oh shit, went zoom, right? Maybe it's a magnetic field or something, and I gave it enough velocity and it went, oh, I'm trying, oh, screw it, and it went flying off that way. Negative velocity, growing bigger and bigger forever. It's crazy. So when is it moving in the positive direction? 0 to 3 seconds. Now, what do I have to do to answer this question? When is it speeding up? What do I have to do? What is it? Sorry? I gotta find acceleration, so I gotta take another derivative. Here's the, let's use this form. That's the most useful form of the velocity. So the velocity is 81 minus 9t squared over t squared plus 9 squared. Have you guys done this one yet? So have you taken another derivative? So v prime is the acceleration. It's yummy. The mistake people make on this kind of problem is you start multiplying shit out. When the question really involves finding the zeros. When is it speeding up? It's going to be when is acceleration. Here's what's funny. Not just when acceleration is positive. So there's another layer to this, but we'll see. You're going to love this shit. Because if I'm going in reverse, that means my velocity is negative. If my acceleration is positive, am I speeding up or slowing down? If I'm going in reverse, which is negative direction, let's say. Let's define it backwards to be negative. And my acceleration is big positive, am I speeding up or slowing down? So I'm getting more and more negative, even though my acceleration is positive. Yeah, that's a problem. So, okay, let's try this again. So if I'm in a car and we're defining forward to be positive and backwards to be negative, and I'm backing up, and my acceleration is positive. So the acceleration wants me to go in what direction? More and more? That way. Yeah.
So it's like you're slowing down.
Yes, I'm going backwards less velocity because my acceleration wants me to go forward. I love it. So when I throw a pen up in the air, right, let's say up is positive, right? And the acceleration, though, is acting against it, isn't it? Trying to draw it back to the center of the earth. The floor gets in the way. Right? So when I throw it up in the air, the velocity is positive, but why is it slowing down? Because acceleration is the other direction. So is it getting faster or slower as it's going up? Of course it's getting slower because acceleration wants it to go the other freaking way. You get this? All right, let's do the first piece. The derivative is the first piece. The second piece is to realize it's not just finding where acceleration is positive, it's finding where acceleration has the same sign as the velocity. That means they're acting in the same direction. All right, Jeff. Oh, to it. Derivative is your first concern. All right, so let's see. Derivative of the top is negative 18t times the bottom minus derivative of the bottom. Give myself some more room. What's the derivative of the bottom? What do you have to use for the bottom?
4t times t squared.
Yeah, I like it. So the 2 is going to come down to the first times the derivative inside, which is 2t. So 2 times 2t, 4t. And now let's do a first power times the top, right? All over the bottom squared. Squared is 4. So there's 2 levels of any math course, to be honest. The nuts and bolts, can you handle the nuts and bolts? And then, can you handle explaining what the shit it means when you plug stuff into it, or just what does the function itself mean? Now, this is where people start going a little insane. They foil this shit out. No. I need to know what the sign, so I need to know where the zeros are of this, which means I want to factor this shit, right? Yes, no, maybe?
Can you say it's 0 though?
Huh?
Can you just say it's 0 as if it's like,
How do you mean?
like if you just plug in 0, negative 18, and the minus 4, it'll just turn it into 0 and then later.
But I don't care about time equals 0.
Oh.
I don't want to make my time 0. I want to see when is my acceleration 0. That's why I want to factor. Just like here, if I factor, I can see when my velocity is 0 at 3 and negative 3. Which here 3 is the only one that makes sense. Okay. I want to do the same thing here. So what's the very first thing I can factor out of the top to help me? And there's a few things I could do, to be honest. Yeah, let me make sure you guys all notice something. What comes out of here? 9. So can't I make this? Well, let me keep it 4. Can I make this 36t? And this will be 9 minus t squared. Right? No? Yes, of course. Right? I just take a 9 out. Times 4 is 36. So now this is to divide by 9, 9 minus t squared. Okay. And then, so what comes out now? I can take a negative 18t out, right? And 1t squared plus 9. I mean, this problem right now, what we're doing right now, should be easy. It has to be easy. It just should be. You should want a lot of this. This is nice. This is algebra. Some of you guys are like, I'm desperately trying to get away from that. Well, you never will. And the trajectory you're on, you never will. It's a part of everything. All I'm doing is a GCF between these two things, right? They both have 18t negative, and they both have a t squared plus 9. So here, I took out everything except one of the t squared plus 9s, right? So there's a 1 t squared plus 9 left from this for this term, because I took everything else out. And then I took a negative 18, so that was plus 2. I took that t squared plus 9 out, so all I'm left with is that 9 minus t squared. All over the t squared plus 9. The fourth, which I can actually now make a cube and just kill that guy. Okay. So what's going on? Where am I losing people? What? Is everybody cool from here to here, just applying the quotient rule? Is everybody cool with that? Speak honestly, because if you're not, at least 7 other people aren't. Trust me, it's not just you. Now, what am I doing? I am factoring this thing. I'm not going to multiply this shit out. That makes the factoring I have to do eventually much more difficult. All right, now I can see a bunch of shit that comes out. Negative 18t comes out. Is everybody cool with what I did here? Took a 9 out, put it here. That's all I did. I just didn't want to rewrite everything. Right? Took a 9 out of this. That's what it would be. And I put the 9 on the 4th, 36. So everybody cool with that part? And now I'm just taking out negative 18t. That's why it's a 2 there. Because that would leave a 2 there. And I took 1 t squared plus 9 out because that's what they both have. Right? GCF. Negative 18t, that. So there's 1 of these left here, and there's a 2, and then there's a 9 minus t squared left there. Yes?
So when approaching problems like this, do you find velocity and acceleration the same way every single time?
Totally. That is a fact. Velocity is the derivative of position. Acceleration is by definition, to be honest. We define the velocity to be the derivative of the position. And the acceleration is the derivative of that. I like it. So that won't change. What's going to change is the function they give you. What function does this thing follow on its little freaky roller coaster ride through the world? In this case, it followed this freaky ass thing. Let's see, where are we? All right. So we have negative 18t times, what's in here now? It'll be t squared minus 2t squared, so negative t squared, and 9 plus 18, 27, all over, who really cares about the bottom? Poor little bottom dude. Bottom's positive, it doesn't really give me any information. So where is the acceleration 0? There's one direct place. That's what this is, right? Acceleration. When is the acceleration equal 0? At t equal to 0. And t equal to 2 little freaky things here. You could solve that, right? It's going to be the square root of 27, and then negative square root of 27. So the negative one we can throw out. So I don't know why it worked. So square root of 27 and negative square root of 27, which we can throw out because it's below 0. So at 0 seconds and at 3 rad 3 seconds. What's the multiplicity of each of those roots? 1. They're each 1. This showed up once. I can factor this using this shit. Each one would show up once. Okay, now. Okay, so the nuts and bolts of this. Everybody can handle the quotient rule twice. You should be able to. Be able to suffer through that. The factoring seems to be kind of more of a problem in general. I mean, across 180s and stuff, I've noticed. It should not be. It really shouldn't be. That should be the part where you're like, oh, good, thank God. Now I just got to do some factoring. GCF most of the time for this kind of stuff. You see this repetition a lot because of the fact that I had t squared plus 9 squared. You're going to see this kind of repetition kind of thing. That's why the GCF is going to be immediate for a lot of these things. So now what I want to do is, this is velocity. What about acceleration? So I have two things. I have 0 seconds, which really doesn't come into play, and 3 rad 3 seconds. Let's see. Let's put it in the right scale. Same scale as this. 3 rad 3 is going to be a little bit bigger, of course. So what's the sign of acceleration here? Well, all I got to do is plug in like a 1 to figure out what it is. And of course, and again, this should be like breathing to you. What's the only place acceleration can change sign? What's the only places it can change sign? We figured it out. Where's the only places that the acceleration can change sign? 0 and 3 rad 3. That should be immediate. So some of you guys are like, yeah, it's immediate. Some of you guys are like, I have no idea what you want. But that's what that means, right? That's the only places they can change sign. So what's a sign in this whole region? I just got to pick a number here. I'm going to pick 1, right? If I plug a 1 in, I can see what the sign of acceleration is.
Can you just look at how the velocity is changing?
I did. It's right there. Yeah. So above, I'm going to do acceleration up here so I can compare them. If I put a 1 into the acceleration, what do I get? I get positive times negative over positive. You guys see, I don't care what the number is. I don't give a shit what the number is. I just care about is it negative or positive, right? So it's negative here. Negative all the way through here. So up here it's going to have to be positive because of the multiplicity. If I put something in above this, like 4, 27 minus 16 positive, and then times, what am I talking about? 27 minus, 4 is not above that, Jeff. Let's try something above 3 rad 3. What would be definitely above 3 rad 3? 8. So 27 minus 64 is negative. Negative 18 times 8 is negative. That's going to be positive. Did I have to do any of that? No. The multiplicity told me it would change sign around its root because it had an odd multiplicity. So it's going to be positive up here. So when is acceleration helping the velocity? When are they going in the same direction? So here, I'm moving forward, right? But my acceleration is backward. This is what you call deceleration. When you decelerate, when you push on the brake, your acceleration is back. If your acceleration was in the same direction of velocity, you would be speeding up. The exact opposite thing you want to do when you hit the brake. So where are they acting in tandem between... Here they're not acting together, are they? Up here they're not acting together, are they? It's in between here that they're acting backwards, right? Here I'm going backwards, and I'm accelerating back. So I'm going backwards, and my foot is on the gas, right? Accelerating backwards. And here's where I go, well actually, look, the acceleration is always back after that. Oh, that's it, boss. Acceleration becomes positive here, so then I'm going back less. I like it. All right, so in between 3 seconds and 3 rad 3 seconds, I'm speeding up. So when is it speeding up? From 3 seconds to 3 rad 3 seconds. that is when it's speeding up. After that, it's eternally slowing down. In fact, what's the limit of the velocity as t goes to infinity?